For all of human history, our connection to the cosmos has been one of sight. We've stared into the night sky, built telescopes to see farther, and launched satellites to capture light in all its forms, from radio waves to gamma rays. Every discovery, every galaxy, every planet we've ever known came to us as a form of light. We were watching the grandest movie ever produced, but it was a silent film. Now, for the first time, we've turned on the sound. We have entered the era of gravitational-wave astronomy, and we can finally hear the universe. We can listen to the most violent, energetic, and hidden events in the cosmos by detecting the vibrations they create in the very fabric of reality. This isn't just an upgrade to our telescopes, it's a brand new sense. It's a revolution on par with Galileo first pointing his telescope at the sky, and it promises to change everything we thought we knew. So what exactly are we listening to? What is this symphony of space-time? To understand that, we have to go back to the mind of one of history's greatest thinkers, Albert Einstein. In 1915, Einstein completely rewrote our understanding of gravity with his theory of general relativity. Before Einstein, we had Isaac Newton's view of gravity. Newton imagined gravity as a mysterious, invisible force, a sort of cosmic string pulling objects toward each other. The sun pulls on the Earth pulls on the moon. It worked well for predicting planetary orbits, but it didn't explain what this force actually was or how it worked. It was just a property of mass. Einstein offered a much more profound and elegant explanation. He proposed that space and time are not two separate things, but are woven together into a single four-dimensional fabric he called spacetime. And here is the genius part. He said that massive objects don't just exist in spacetime, they actively distort it. The classic analogy is to imagine spacetime as a vast, taut rubber sheet. If you place a bowling ball in the center of that sheet, it sinks down, creating a deep curve in the fabric. That curvature is gravity. Now, if you roll a smaller marble nearby, it won't be pulled directly by the bowling ball. Instead, it will simply follow the curved path that the bowling ball has created in the sheet. The marble is trying to travel in a straight line, but the space it's moving through is curved. That is exactly what's happening with our own planet. The sun, being incredibly massive, creates a huge warp in spacetime around it. The Earth isn't being pulled by a force from the sun. It's simply following the straightest possible path through the curved spacetime created by the sun's mass. We perceive this path as an orbit. General relativity explains why planets orbit stars, why galaxies hold together, and why an apple falls from a tree. It's all just objects following the contours of a dynamic, flexible universe. But Einstein's theory didn't stop there. His mathematics revealed something even more startling. If a massive object just sits there, it creates a static curve. But what happens if that massive object moves? Specifically, what if it accelerates, if it changes its speed or direction? Einstein realized that accelerating massive objects would create ripples in the fabric of space-time. Much like moving your hand up and down in a pond creates waves that spread across the water's surface. These ripples are not waves traveling through space. They are waves of space itself. Space-time itself is stretching, squeezing, and oscillating. These are gravitational waves. Now you might be wondering, if any accelerating mass creates these waves, why don't we notice them all the time? I am waving my hand right now. Am I sending out ripples through the cosmos? The answer is yes, technically, you are. But the effect is so infinitesimally small that it's completely undetectable. Gravity is actually the weakest of the four fundamental forces of nature. To generate gravitational waves that are strong enough for us to even hope to detect, you need events of truly unimaginable violence and scale. We're not talking about waving hands or even exploding stars. We need the most extreme, compact, and massive objects in the universe, moving at incredible speeds. The primary sources of detectable gravitational waves are cataclysmic collisions between black holes and neutron stars. Imagine two black holes, objects with so much mass crushed into such a small space that not even light can escape. locked in a gravitational dance. They orbit each other, getting closer and closer, spiraling inwards at speeds approaching the speed of light. As they accelerate around each other in this frantic death spiral, they are churning the fabric of spacetime, sending out powerful, continuous ripples, gravitational waves. In the final moments before they merge, they release more energy in the form of gravitational waves than all the stars in the observable universe combined release as light. It is the most energetic event in the universe since the Big Bang. When two neutron stars, the collapsed, ultra-dense cores of giant stars, collide, they create a similar cosmic spectacle, sending out another blast of space-time ripples. These are the events we are now able to hear, the true symphony of space-time. So we've established what creates these waves, but what are they actually like? They have a few key properties that make them both fascinating and incredibly difficult to detect. First, they travel at the speed of light. This was a major prediction of Einstein's theory, and its confirmation was a huge blow to the old Newtonian idea that gravity's pull was instantaneous. If the sun were to suddenly disappear, we wouldn't feel the gravitational effect for about 8 minutes, the same amount of time it takes for its light to reach us. Gravity moves at the speed of gravity, which is the speed of light. Second, their effect is physical. Even though they are invisible, as a gravitational wave passes through you, it literally stretches and squeezes the space you occupy. If a wave were traveling towards your screen right now, it would first stretch the screen vertically while squishing it horizontally, and then a moment later, it would squish the screen vertically while stretching it horizontally. It would oscillate like this for as long as the wave was passing through. The problem, and the reason it took a century to detect them, is that their effect is almost unbelievably weak. The processes that create them are the most powerful in the universe, but space-time is incredibly stiff, and these events happen millions or even billions of light years away. By the time the ripples reach Earth, they are faint echoes. How faint? A typical gravitational wave detected here on Earth will stretch a 4-kilometer-long detector by about 1/10,000th the width of a single proton. Let me say that again, 1/10,000th the diameter of a proton. This is arguably the smallest measurement humanity has ever attempted. It's equivalent to measuring the distance to the nearest star system, Alpha Centauri, 4 light-years away, with an accuracy smaller than the width of a human hair. The engineering required to detect such a tiny change is one of the greatest technological achievements in human history. But here is the most important property, the one that makes all this effort worthwhile. Gravitational waves pass through matter almost completely unhindered. This is their superpower. Light, our traditional tool for astronomy, can be blocked. If a giant cloud of cosmic dust sits between us and a distant star, we can't see the star. Our view of the center of our own Milky Way galaxy is obscured by gas and dust. We can't see what's happening inside a star or a black hole. Light gets scattered, absorbed, and blocked. Gravitational waves don't have this problem. They will travel through planets, stars, dust clouds, and entire galaxies as if they weren't even there. This gives us a perfectly clear, unobstructed view, or rather, a listen, directly to the heart of the most extreme events in the universe. We are no longer limited to studying the photons that manage to escape a cosmic event. We can now listen to the underlying gravitational vibrations themselves, giving us direct information about the masses, spins, and mergers of objects that are otherwise completely dark and hidden from our view. This new ability is what makes gravitational wave astronomy so revolutionary. Think about it this way. For centuries, our entire understanding of the sky came from what we could see with our own eyes. Then, in the early 1600s, Galileo Galilei built a telescope and pointed it at the heavens. Suddenly, the universe exploded in complexity. He saw that Jupiter had moons, proving not everything orbited the Earth. He saw that Venus had phases like our moon, supporting the idea that the planets orbited the Sun. He saw that the Milky Way was composed of countless individual stars. The telescope didn't just give us a better view, it fundamentally changed our place in the cosmos. It was a paradigm shift. We are living through the next one right now. The first successful detection of gravitational waves in 2015 was our Galileo moment. We have opened a new sensory organ to the universe. We are no longer deaf to the cosmos. This new hearing allows us to probe the universe in ways we never could before. We can test Einstein's theory of general relativity under the most extreme conditions imaginable, in the warped spacetime right next to a black hole. We can study the exotic matter inside neutron stars, which are so dense that a teaspoon of their material would weigh billions of tons. We can pinpoint the locations of cosmic collisions and then point our traditional telescopes there to see if there's any light or afterglow associated with the event, a new field called multi-messenger astronomy. Perhaps most exciting of all are the discoveries we can't yet predict. When Galileo looked up, he was hoping to get a better look at the planets. He had no idea he was about to help rewrite humanity's entire worldview. In the same way, we are listening for the echoes of colliding black holes, but we might hear something completely unexpected. We might hear the ripples from cosmic strings, theoretical defects in space-time from the early universe. We might even hear the faint residual hum from the Big Bang itself, the ultimate sound of creation. For millennia, we have looked at the stars in silent wonder. But the universe is not silent. It is full of sound. It is a chaotic, violent, and beautiful symphony of colliding worlds and vibrating space-time. And after a century of theory and a lifetime of effort, we have finally built the right ear. We are just at the beginning of this new journey, and the universe has only just started to tell us its secrets. The next few decades will be an incredible time of discovery as we listen ever more closely to the symphony of space-time.